Hey everybody, this is going to be the buffer video from the end of chapter 10. I'm going to walk us slowly through the 3 parts of a buffer problem. So this slide is right after we worked this problem with pKa values, and this picks up towards the end of chapter 10. So find this slide in your lecture slides or just take really good notes. But what you see right up here is a generic equation of a weak acid and its conjugate base. Okay, so this would be the weak acid. This would be the conjugate base. And we said these are the 2 components of a buffer. Okay, buffers are not made from strong acids. They're made specifically from things that have a good equilibrium. So then this other equation at the top is known as the Henderson-Hasselbalch equation. You will be given this equation on exam 4. And essentially this allows us to calculate the pH of a buffer. And this equation is only for buffers. Okay, if you have another type of problems where it's asking you to solve for the pH of some acid, and it specifically does not say that you're working with a buffer, you cannot use this equation. You have to use another equation for pH. But this one is only for buffers. So it says pH equals pKa. Okay, so P of Ka is just the negative log of Ka, any Ka value, plus the log of the concentration of A minus we labeled as our conjugate base, so that always goes on top, and then over the concentration of the weak acid, and that always goes on bottom. So here is part 1. Part 1 of a buffer problem is always just asking you to solve for the pH of your buffer. It's not adding anything or taking away anything. We're just solving for pH. So it says, what is the pH of a buffer solution made with 0.1 molar HF, okay, and 0.12 molar sodium fluoride, okay? And then it says the Ka of HF, hydrofluoric acid, is 3.5 times 10 to the minus 4. Now the first thing you have to decide is which component here, HF or NaF, is my weak acid and which is my conjugate base. And there's a couple of ways you can figure this out, but whatever the Ka value is for, okay, the Ka given, that's the weak acid, okay? You can only have Ka values of weak acids. So HF here is our weak acid. So this concentration right here will be plugged in on bottom. And this concentration is our sodium fluoride is our conjugate base. So this will be plugged in on top when we do our equation. All right, so we're going to solve for pH. And the first thing we need, now that we've decided what's our conjugate base in our weak acid, is to get the pKa. So the pKa is going to be equal to, remember P is just a mathematical function that stands for the negative log. So pK is going to be the negative log of the Ka value, which is 3.5 times 10 to the negative 4. So when you do that, I need to grab my calculator. Negative log of 3.5 times 10 to the negative 4, you should get that pKa equals 3.4, if you actually round, it's 3.46. I think in class today, a lot of people are saying 3.45, but technically rounding should be 3.46, okay? So now that we have pK, we're just gonna plug everything into our equation, which is the Henderson-Hasselbalch equation. pH equals, plug in pK, 3.46, plus the log of the concentration of conjugate base on top. So the sodium fluoride is the conjugate base, so I'll plug its concentration in on top, over the concentration of weak acid. The hydrofluoric acid, HF, is the weak acid, so I'm going to plug in 0.1 molar on the bottom. And when you do this, you get that the pH equals 3.554, okay, with rounding. So there is our pH. That's part 1 of a buffer problem, all right? Part 2 and 3 of a buffer problem will always look at what happens when you add a certain amount of acid or base. And it doesn't matter what order, acid first or base first. Here on this slide, we are going to be adding 0.02 moles of NaOH, and this is a strong base. So the question is, what is the pH? And so since it's a buffer, again, we're going to be using this equation. We want to know what the pH of this buffer is after it reacts with and neutralizes all of this strong base, all the NaOH. And the first thing you have to notice is that your concentrations of weak acid and conjugate base are given to you in molarity, capital M. But the quantity of NaOH is given to you in moles. And we cannot add or subtract moles from molarity. So we need to first, always step one, is convert or find the molarity of, here, the substance being added. So here would be the NaOH. So always step one, find the molarity of any acid or base that is being added to your buffer. So molarity is just moles of NaOH over liters of solution, liters of buffer. Now these numbers that I'm about to highlight in, hopefully you can see this, green, 1 liter and 0.2 moles, these are subject to change. They could be anything. It could be 0.5 liters, it could be 500 milliliters. I could give you 1.2 liters. I could give you, 0.025 moles. I could give you 0.2 moles. It's any numbers that I give you. You just need to plug them in and solve for the molarity of NaOH, all right? So to do that, this is going to be equal to 0.02 moles over 1 liter, okay? So the molarity is 0.02 molar. Now, do not think that the molarity here is always going to match your moles. If you have 1 liter of buffer, then it will, but if the volume is different, then it won't. So always plug these numbers in and calculate what your molarity is. Step 2, now that we've done that, is to set up an ice chart. And an ice chart is going to track how the concentrations of my weak acid and conjugate base are going to change. And they're going to change because they're going to neutralize this NaOH. And how that happens goes all the way back to our buffer diagram. Okay, so I'm going to real quick take the time to draw this out. We have weak acid in equilibrium with conjugate base. Now, I want to point out right here that sodium sodium is just a spectator here. It's not actually involved in the reaction. So if you were to just write the conjugate base as being F minus, that is perfectly acceptable, okay? Because sodium is really, it's just kind of a filler. It's not part of the reaction. The real true conjugate base is just F minus, okay? I hope that's not throwing you off, but it'll make sense when I draw this diagram out if you just see F minus. It'll make a little more sense. So we have NaOH, which is aqueous, and in solution it will break up in Na plus and OH minus. And OH minus is really the strong base component here. So OH minus is coming in, and it's saying, you know what? The more OH minus that's around, the more I'm going to raise the pH. But because this is a buffer and we want pH to be maintained and not to change, this weak acid right here, HF, is going to neutralize OH minus. And it does so by donating its H plus to OH minus, okay? And when we do that, what do we make? We make water. We have neutralized OH minus, all right? Now what's left over, if HF here splits apart into H plus and F minus, okay, which is what it's doing to donate a hydrogen ion, what's left over when it does that, inherently, we create more F minus. So what is going to happen is we're going to lose some HF. It's going to sacrifice some of its molecules to go neutralize any hydroxide ions that it sees. So the concentration of that's going to go down. The concentration of F minus is going to go up because inherently we're going to make more every time we neutralize the hydroxide. Now, these little arrows right here are going to indicate to us how we fill in our ice chart. So I'm going to come back to those in a second, but write out your ice chart and write the weak acid and the conjugate base at the top here. And I stands for the initial concentrations of these things, which are given to you right here and right here in the problem. They'll always be given to you. And these will be the same numbers that you plug in. 0.1 molar here and 0.12 molar there. Okay, please put your units of molarity, capital M. Now, the arrows that I just drew are going to tell us whether we add here or whether we subtract here and add here. Okay, so let's see what makes sense. If we are using up HF, then and the concentration of it is going down, decreasing, that means when we add base, we're going to subtract from this column. And since the arrow for F minus means we're going to make more of it, it's going to go up, then we're going to add to our conjugate base column. All right? So again, what I was saying in class, and a kind of a maybe hopefully helpful way to remember this is, let me see, what color do I want? Maybe y'all can see purple. When I add base, I'm going to add to the conjugate base column. When you add base to your buffer, you're going to put a plus sign on the conjugate base column. Okay? I hope that makes sense. Maybe, we'll see. So we have a plus and a minus in the right spots. Plus and minus what? By how much? It will go up and down by the concentration of the base or the acid that's being added. So you'll plug in 0.02 molar here and 0.02 molar here, right? And then you're just going to calculate these columns. 0.1 minus 0.02 is going to be 0.08 molar. And then 0.12 plus 0.02 should give you a 0.14. E stands for the new equilibrium concentrations that you now are going to plug into your Henderson-Hasselbalch equation. So we have everything ready to go, and now we're going to solve for what the new pH is, because that's what the question's asking. Remember, what is the pH? So that's what we're trying to solve for. So it says pH equals pKa. Is my pKa different? The answer is no. You're going to use the same pKa throughout every part of the problem. So you just go back to that initial calculation, plug in 3.46 plus the log of conjugate base, so the 0.14 molar, over weak acid, 0.08 molar, okay? These concentrations get plugged in right here. Now, when we recalculate this, 3.46 plus the log of 0.14 divided by 0.08, you get a pH of 3.70. So initially, our pH was 3.54. And when we added NaOH, the pH did go up to 3.57, but it didn't go up by much. So what that means is our buffer did a really good job of maintaining pH around its initial pH while neutralizing all of that NaOH added. Okay, so that's part 2 of a buffer problem. The last part, since we've already looked at what happens when you add base, now we're going to look at what happens when you add 0.02 moles of HNO3. And if you go to that big chart that has a bunch of acids and bases and their strengths listed on it, you will see that HNO3 is a really strong acid. Okay? So the first step, again, just like we did with the NaOH, is we need to calculate the molarity. Right now we just have moles. Moles and molarity are different, so we're going to get the molarity of HNO3, which is going to be, you know what? Just because I'm going to change this up. I just don't want y'all to think it's going to be the same number every time. What if this was 0.25? And what if, you know what, we did have 1.2 liters, okay? I'm going to use these numbers instead. So make those edits to your notes. I just don't want you to think it's going to be the same numbers every time. So now we'll just go 0.025 moles over 1.2 liters. And what do we get? 0.025 divided by 1.2. We get 0.021 molar. Okay? So that's the concentration of HNO3 that's being added. And now I can do my ice chart because my units for HNO3 match my units for my buffer components. So step 2 is set up your ice chart. So I'm going to write my weak acid and my conjugate base. And the initial concentrations, again, they're the same as they were last time. These do not change. So my initial concentrations would be 0.1 molar and 0.12 molar. Now, how should I write in my change row? Well, this time, let me zoom in over here. Here is our buffer diagram again. And we have a really strong acid that's going to dissociate into H plus and NO3 minus, okay? That's what nitric acid, this guy, will dissociate into. All right, and which one of these components is going to go into action to neutralize the acid being added? So again, think to yourself, do acids neutralize acids or do bases neutralize acids? And the answer is that bases. So the only bases neutralize acids. So the only base we have present here is our conjugate base, F minus, is going to swoop up, react with this H plus, and when it does so, what does it make? It makes HF, all right? HF is a weak acid and has very, very little ability to change, especially since we already have some of it in our solution, to change the pH, unlike a very strong acid. So what that means is that the concentration of HF is going to go, just use a different color, it's going to go down. We're going to sacrifice some of our conjugate base to neutralize the acid. And inherently, we're going to make more weak acid in doing so. These arrows let us know how we should draw in our plus and minuses. Since HF is going up, we're going to be adding here and subtracting here. So when you add acid, you add to the acid column on your ice chart. All right, by how much? The concentration of acid being added, 0.021 molar, 0.021 molar. So now we just subtract off and add and subtract as our chart tells us to do. So we should have our equilibrium concentration of weak acid, HF, should be 0.121 molar, and the new equilibrium concentration of NAF, our conjugate base, should be 0.099. Is that right? Yeah, molar. These we're going to plug into the Henderson-Hasselbalch equation, which is right up here. And you'll have this on the exam, so you do not have to memorize it. So now let's just solve for pH. pH equals pK, same pK that we've used the past two times, 3.46, okay? 3.46 plus the log of conjugate base on top, so the 0.099, over concentration of weak acid, 0.121. So now we just plug all this in to our calculator. And we see that our new pH, once we have neutralized all the HNO3, is 3.37. So the pH dropped. The initial pH was this 3.54 when we added base. It was raised up to 3.70 when we added acid. It dropped to 3.37, but it is maintained around 3.5. So not bad. You can see that a buffer problem is a lot of work, okay? Lots of steps, so they're worth lots of points, okay? Now the good news is that it's separated out into 3 parts, but the bad news is it all kind of builds on itself. So you miss part 1, you're going to miss something on part 2. But these questions, of course, would be partial credit. So if you forget one little thing but know how to do the rest of it, you would get most of the points. So please reach out if you have questions. I hope this was helpful, and that is a buffer problem.